Hi, today we're going to talk about not fixing the symptoms of a problem and actually learning to do classic real-world performance. And within the real-world performance group, we always take pride in taking a top-down view of the problem rather than debugging a problem from the bottom up. And this is a big challenge that we face in our industry, particularly in IT departments that are heavily segmented and very often don't communicate well with other departments, and everybody's working defensively to make sure that everything looks good from their perspective. And people aren't learning to look holistically across the whole depth of a system to see how we can increase the whole system performance. And this is a big challenge within today's IT organizations. And it's something that I take great pride in that the Real World Performance Group does, is that we look holistically over the whole stack and see what can be done to improve the whole system performance. And this is extremely important. And what we have is a very simple demo that we're going to show, and it probably is being panned out and played out the similar situations in multiple companies, in multiple industries, in similar applications all around the globe. And people are scratching their head thinking, how do we increase performance? And a lot of people are making lots of suggestions, but they haven't yet figured out what the problem is. And this is something that we see daily, with this desire to be fiddling with things, changing things, but really no sort of understanding of what the big picture problem is. So on this system that we're looking at today, it actually it's processing records coming off a manufacturing facility. Basically, barcodes on devices are going through on testing equipment and manufacturing equipment, and it's generating a log, and it's producing manufactured goods. And all those manufactured logs and things like that are going into flat files, and then we have to load those files into a manufacturing database such that we can figure out how efficient is the production line running, what's our defect rates, is there a genealogy associated with bad machines that have a higher error rate and things like that. But this could be the same as in many other applications. This could be your telephone bill. This could be an online application where all requests are coming from a single browser. It likewise could be from a government and agency processing tax returns or tax forms and things like that. There's so many times we have seen this occur within the real world, yet we have seen a lot of very smart people focusing their effort, literally trying to do bottom-up debugging, fiddling around with database parameters, and actually having absolutely zero success of raising the real-world performance number, which is the business transactions that they push through their system. And so this is just hopefully a bit of a wake-up call and an education. When we actually built this demo, we were surprised at the performance gains that we can achieve by just doing the basics of good computer science and doing a top-down analysis. So maybe I should introduce the system. It's a workload that is loading manufacturing data from a series of flat files, and the application is basically reading the flat files and then basically hashing the data of each row to a number of application servers, and it's doing this as a means of load balancing everything. All the work that happens and all the rows that arrive are load balanced across the application servers, which is what you can see with the red lines there. And then the application servers load balance across to 2 instances within an Oracle database. Now let's have a look at the performance of this system. And by the way, this is not good performance. This is our start. This is our entry point at the start of the analysis. You'll notice that the transaction rate is about 8,000 transactions a second, maybe closer to 7. You'll notice we're spending a lot of time waiting in the app server. The database response time is getting close to 40 milliseconds. And if we actually start looking at the ASH report or the AWR report, you can see that we're actually not spending much time at all on the CPU, which would be that thin green line at the bottom. bearing in mind we've got 2 instances. But boy, are we spending a lot of time in sort of rack related cache fusion events, moving blocks back and forward between database instances. So at this point in time, people were thinking, well, what's going on here? The database doesn't scale. So perhaps we can just go a step through and just start to understand the problem. People are saying, oh, perhaps we need to rebuild the indexes, hash partitioned, reverse key indexes. People are saying rebuild the indexes with higher percentage frees, reset initrans to a large number. But for the sake of this analysis, we're not going to actually change anything on the side of the database. We're not going to change any storage clauses. We're not going to change any table definitions. We're not going to change any index definitions. And we're just going to use some real-world principles to actually identify what the problems are and then work them out of the system up the stack in the application layer, because we believe that's actually where you can make the most difference. So the first thing we want to do, because it's all so confusing with all the clustering, is we're actually going to start running the system literally on a single instance. And let's just see what happens there to the system. We certainly expect all those gray wait events to disappear because we're redirecting all the workload now down to a single instance. And you can see just by redirecting the workload to one instance, we've actually increased the performance quite dramatically and the response time has come down. But you can see that this really isn't the total answer, because we're still not getting that good utilization within a single instance. We've still got a lot of contention within the system. We've got latch contention here, but we've also got index contention and buffer busy waits still within a single instance. So perhaps we still, although we've moved the workload around and shuffled it about, we still don't understand the problem. But let's have a look and think what we're doing with the workload. We're still doing a lot of load balancing and shuffling all the data across all the application servers. Now this file contains all the instrument readings for a single serial number of a process, of an object being manufactured. Likewise, it could be your tax return, it could be your phone number, it could be basically your browser IP address if you were doing an online system. So we're basically redirecting all your requests pertaining to a single element of data or something, a cluster of data, across multiple application servers. Now let's think about that if we could actually just get some affinity between that part and an application server. Let's think of the impact that that might have on performance. Getting some affinity up the stack, and instead of trying to load balance all the manufacturing data for one part across app servers, how about just stream it to one app server? Likewise, all requests coming from a browser, instead of trying to load balance them across multiple app servers, let's try and affinitize it to one app server. So let's try that, and let's just show affinity to within an application server. Now what we should see is we should see that crossed red line disappear. And now we're starting to see that we're really actually starting to make a bit of difference to the performance, because we've actually, what we've done is we've actually, in this case, halved the number of processes all fighting for the same data that was being fused either between 2 instances when we were in the rack case, or contention for the same blocks within a single instance. So we've taken the performance up from less than 8,000 transactions per second, but we're now getting it up into the 30s, and we haven't changed a single thing in the database at this point in time. All we've done is redirect everything to a single instance at this point, and then got some affinity between the application and an application server. Now, each application server has multiple threads, and we're still load balancing amongst those threads within an application server. So the next logical step would be to get some affinity between that data and just one application server thread. So if we were manufacturing a piece of equipment, every bit of data associated with that piece of equipment, if that was all to go through one application server thread, there would be no contention on that data from any other threads. So let's try that. And we'll do what we call full affinity. This would be the same as if we had a browser. So we would redirect and get some affinity that all requests from a single browser would just go down one application server thread. Now you can actually see that we're really starting to move, and in fact the red and blue lines are now showing that we're doing a lot more throughput on these sort of things. And you can see literally by getting affinity we've removed a lot of the contention, and we can see that we've taken the throughput here literally up to 65,000 transactions. We're nearly 10 times faster than we were when we started. Okay, so this gets to the point where we've learned that if we stop trying to hash everything over everything and load balance everything over everything, by doing all that load balancing, what we are actually doing is we are initiating contention at both app server and database level, and we're also diluting our ability to get good cache hits to find the data in your local cache. So the last move on this move is, instead of having a connection where all app servers connect to all database instances, if we were to map the app server to a specific instance, we can get to the next point, and then we can fully utilize all the hardware. So now we have a dedicated service where each application server maps to its own database instance. You can see that the performance at this point, we've now taken it up to twice what we were achieving with a single instance. We're now at about 125, 130 transactions per second, which is more than 10 times that we achieved when we were load balancing everything over everything. Okay? Now, it may look smart in an architectural diagram to load balance over everything, but all data by its nature tends to have some sort of clustering ID. So if we can route things through the middle tier, clustering on that data element, now that could be your social security number, your telephone number, it could be a serial number of a part, all those sort of things, or even your browser IP address, we can actually affect some affinity at the database level, and it comes back to that old-fashioned idea of, if you can be modifying your data in your own local cache, it's 1,000 times faster than if you have to get it either from another instance or from disk. And you can see, as a result of getting better affinity through the system, we have made the performance go from 8,000 transactions a second to nearly 140,000 transactions per second. You'll notice we didn't change anything on the database. We didn't change a storage clause, we didn't rebuild an index, we did absolutely nothing at the database level. We just basically refined the workload coming through the middle tiers such that we could get good clustering of data. Now, this doesn't have to be an exact solution. This is by no certain an exact solution, but if you can get clustering through the middle tier and you get it right 9 times out of 10, you're going to be doing better than you do it 5 times out of 10. If you can get it correct 99 times out of 100, you're going to do better. But you're no way, in modern applications, are far too complicated to ever get this to be exactly 100%. But if we can get it into the 90s, we're doing really well. And this is really important that it is understood that you can kill systems performance by trending to hash everything over everything, load balance over everything. And we actually know this in real life. If we keep all the data that we want to process together instead of spreading it out, we always can do that performance. It's very simple. If we were basically to put all the data we needed over 16 desks, it would take a lot longer to process. If you put it all on one desk, you could process it together. We all know this stuff. So with that in mind, you can see we've built a high-performance system that's doing a high throughput, but it's sensitive. People need to be educated as to what you're doing. Architects need to think about data affinity through the middle tier. And this can be degraded by literally somebody not quite understanding what's going on. And if suddenly they decide to say, oh, I'm going to use a different connect string, and perhaps we'll use something like the scan listener, thinking they're going to load balance it, they can devalue the whole thing straight away. Because you can see fairly quickly, we're now trying to load balance. We think we're logically load balancing over instances, but we're now degrading our cache affinity, and so back come the gray wait events, and the system throughput has been halved. So you can see, by not touching anything at the database and just trying to ensure better data affinity coming through on the transactions, we can have dramatic impacts on response time and on throughput.